simple kinematics, which means minimal sim to real gap. Absolutely, I believe, I didn't even have to see that statement to agree with them because I already knew, wait a minute, you get rid of all those problems because tendons are going to be very difficult. Again, you want to get a plinking kind of movement like that with my finger. The number of tendons that you need to be able to move and coordinate gets very complicated. If you kind of look at that fist and look at your own, when you make kind of a similar kind of fist, it looks very close because you see how it slopes down. Many other robot ones, you look at that and they're very straight. They're very horizontal with everything else. They just don't look natural. So this is your flexion. So that is in basically the same direction as the flexion on the PIP and the DIP. So you pretty much have three kind of flexion joints going on at the same time there down at the MCP. What's rather interesting is that the abduction in this case is happening between those flexions. That's unusual. On all the other robot hands, usually the abduction comes first, then comes the first flexion, then the PIP, and then the DIP. And so in this case, as we can see, it's down just underneath it. Ideally, you want them to line up. You would like to kind of make a spherical joint there, but how are they accomplishing the flexion? Because it's not clear. There's no kind of simple sort of motor in there. It seems like an absence of anything in there. And the key is focusing on these two black screws in the back, these screw heads that I've circled in red to give you an idea. And the hint is, it tells us that what they probably did is they built a small 4-bar linkage in here, a parallelogram 4-bar linkage, where the flexure motor is down here somewhere, and you have sticking out here, which would be a lever arm, with a connecting one to the other lever arm. And I was telling you about that black piece that's up there. That's one big piece, and which has a lever that sticks out over there. So here's the knuckle. And in here in the red part is something that we can't see. So back behind there is a pivot point, and we can sort of see what looks like a linkage mechanism going between here and there. And we have a rotation in green, another rotation point in blue, and another one here in purple. And if you look at this, don't be thrown off by the fact that this has kind of a dog leg in there. All that matters is the geometry between them. Okay. So we have these points. So now you can see what makes the linkage. And when they rotate it down here, they can get, and that way they could have like a big output shaft that just doesn't fit up there. It was just going to get in the way, and they can move it down there to get that kind of movement. This is impressive. If you might remember in the video, this is just a snapshot of what's going on as a reminder. They basically took a weight, and with just a 2-finger grip, and that was a 5-kilogram mass, they were moving it up and down without it flopping around. Okay, so hi Marwa, how are you doing?
I'm doing good. How are you, Scott?
Good. It's been a few weeks since we've been able to do the podcast because we've been busy and traveling and everything else. And in that interim, there's been, let's say, a lot of rather interesting developments coming out of China regarding what I refer to as the business end of the robot, which we all know is the hands. And it seems like, almost every day, if not every week, there's yet another Chinese company that is revealing some sort of new hand. And we haven't been able to cover all of them. Some of them are more kind of consumer grade ones because they're like just 11 DOF ones that they're trying to get out. So maybe some hobbyists or people doing startups can work with it. But there's some other that are more advanced that might actually be very interesting than humanoid bots. And so we're going to go ahead and take a look. And so do you know which hand I'm talking about?
I think the Chinese one that I think have been a lot of buzz around it.
Right, right. It's kind of one in particular, and I'm so rusty here, I can't even remember how to share my screen. So let's go ahead and try that. So here we go. This is the Wuji Hand that comes from, well, they're calling themselves Wuji Tech, but it seems like it's part of Pan Motors, which is a company that was founded, I think, in 2019 to actually make small high torque motors. And they developed a hand that has got quite a bit of a buzz. Now, I sort of referred to that over the past month or so. There's been a couple other rather interesting hands that are worth a deep dive on their own. This one coming from We Robotics out of Korea, which is called Alex. It's actually the Alex robot. It's an upper body torso. So it's more than a hand. It's really a forearm that has a lot of other things. It seems to be mostly tendon driven. with maybe some other linkages in there. So it's kind of a hybrid approach. And then last week, there was also another bot out there. Whoop. And this is from Dexel Robotics, the Apex hand, which is also rather interesting. And they gave a lot of detail about that. Also worth a deep breakdown. And it's also a tendon-based hand. Uh, and actually, I did a pretty deep dive already in those two hands over to Royden's channel, Over the Horizon, with Royden and Gustav Anderson. But the one that everyone's really been talking about and sending me a lot of notes is like, "Hey, what do you think of this?" is the Wuji hand. Now, this is not tendon driven, so you might say, "Oh, is that a first?" Like, no, no. There's plenty of hands out there that are not tendon driven, but they're using like mechanical linkages, and they're putting pretty much all of the motor drives actually in the palm. And because of that, they're limited. So they might have, 5 or 6 actuators in there and do the linkages or get everything to move. What's interesting about this is the number of degrees of freedom and the number of motors they put in there and how they've done it. And there's some others that have used micro drives, but these are different. So just if anyone wants to know what Wuji stands for, you know what Wuji stands for?
No. No, what does it mean?
It's it can translate into a lot of things, but mainly it means like almost like absence of nothingness or infinity. It's a bunch of things. you know? So it could be like the infinity hand, and I think it also is used in like martial arts and a bunch of other things. But interesting choice of name. So I guess it means like infinite possibilities that you'd be able to have with it. Okay, so um, another thing, the background of the company, it's Wuji Tech. If you want to find out more information, you'll find the website is like panmotor.com, where there's some other information that's not included in the video that is kind of supplemental. So you can find out a little bit more about that, the background. Anyways, this is the video itself that came out. And as you can see, it seems to have a certain amount of dexterity. That's the teaser leading up. And we get some pretty nice close-ups. We've seen hands that have gloves that are very manipulative, but we can't see what's behind the gloves. So I'm really impressed that they let us have a look here. And some of the things that are coming up on the screen, we'll go into the details on those at first, but I want everyone to appreciate a little bit of what's going on with the hand, to see how it, as a pretty good skeleton when you put a glove on it, how it really looks very human-like, and the kind of movements that are going on here. So, man, exquisite details going on here that we're going to be able to break this thing down. Of course, I made tons of screenshots, tons of notes, and everything about this. This here, we're going to be referring to this is like a type of Kabunchi score, which is probably higher than you would normally do. It's showing the amount of dexterity. Again, the abduction, which is very important. And they mentioned there are 20 rotary actuators, which means this is a 20 degree of freedom hand, which has actually 20 motors. And that's unusual because a lot of times you'll hear like Tesla has an 11 DOF hand, but I think 6 actuators that are in there. I believe Figure is like a 16 DOF hand, and they also have like I think 6 actuators that are being able to do it. So a lot of times the number of joints, which some people call degrees of freedom, does not equal the actuator count. In this case, it's 1-to-1, which makes it extremely interesting to see what's going on. Now we're going to look at some of these gestures that they have in capabilities and demonstration to see how impressive they either may or may not be, but it seems to be leading in a rather interesting direction. And that's why I've had a lot of interest on it. So anything that you notice that's rather interesting?
I feel like that had more resemble human hand than dexterity. It feels more
It's
bulky. It feels
it
a real
yeah,
hand.
it seems very, and look, it's all there. There's no forearm. Everything is built in to the hand itself. So they actually use the space in the fingers to put everything. And the question is, well, excuse me, can you actually make a drive small enough to have the torque to be able to do that and still be able to fit in there? And that's what everyone wants to be able to do. And this is like the kind of the first demonstration of properly doing it. And I'm going to go into some of the different approaches everyone else has taken to try to do the same thing and why this seems to be one of the best. Now, the one thing I kind of note here is again, a lot of the things we're seeing these videos coming out the past couple of weeks, they're showing like the same thing. The scissors, the Kapuni, and here how durable it is. And that means if it punches you, it's going to break a bone. And again, looking at the precision capabilities here, that's also pretty impressive and something that's not easy to do repeatedly with a tendon, especially over time. You can usually pass that test really early, but over time it might become a bit more difficult. So Very interesting hand. Some great detail. I'm actually quite impressed with the amount of detail that they've provided us here. So, oh, and I want to go to the next slide here, which is right there. All right. So, one of the first things about the hand is that it's lightweight. Okay, so it's under 600 kilograms, which is pretty decent. Um, and there's no other forearm that you need to worry about having, the mass in there or anything like that. So that's working quite well. Okay, super dexterous. So what's interesting about this is that, they say no couple joints fully articulated. And when you have a tendon-based hand, your fingers, your knuckles or your IP joints are basically coupled. So you have one actuator moving and it's causing the entire finger to move. So that means you do not have control of the individual IP joints. Because
Mm,
they have an actuator per IP joint,
mm.
it gives them unprecedented degrees of control on the finger. So that's rather impressive. Um, and I threw this thing in here to remind us because I've forgotten before. This is a 20 DOF hand, so 20 degrees of freedom, and actually 20 joints, however you want to look at it. So they have 20 actuators in there, and they're all rotary. It's a misspelling there, but they are rotational actuators. Um, Fairly decent payload. So the tip force of 15 kilograms. If you're not familiar with physics, divide that by gravity, which is about 10, 9.8 is equal to 10, 1.5 kilograms of basically force that you're going to there, if you want to think of kilograms as force. And then a static grip load of 20 kilograms, which is pretty good. It's pretty decent for hands like this. And as we keep on saying, this is the worst they're going to be. It only gets better from here. Okay, so true to human anatomy, so they're really trying to scale it so that it's not too big and too small. A lot of the hands out there might be almost oversized. It's it's kind of close to human anatomy. I prefer to say it's truer to human anatomy than others, and we're going to get into some of the reasons why. There's definitely some room to improvement, but they're moving in the correct direction. Okay, so one of the first things to look at is that when you look at your hand, you notice there's a nice arch along the top. And basically, your middle finger is the longest finger. And then you have, your index finger, which comes a close second, and everything else makes that nice arch. And so each finger has a different length, and you can see they're all the same length. So they haven't made them different. And the trick to doing that is, of course, is along the palm. You have an arch along your palm, which can also help
Yes.
out in being able to do that. And there's certain ways of doing it. If you actually look very closely in the palm, you'll notice that your index finger is actually a little bit below the middle finger. And you'll see in this case, they actually got it a bit too high. And I think I kind of know why.
Mhm.
That's a problem. So it would be nice for them to get the finger lengths different, but that may be a little bit different because they're making them out of these little Lego blocks, which are
Mhm.
the motors and everything. So they're starting out. I have a feeling they'll probably change that in due course. So they're trying to do a little bit on there, and it's sort of a shame they do it because if we actually look at a real human hand, we'll look at this, and you'll see the metacarpals that are in here. The second metacarpal, which goes over to where your index finger is, that one actually sometimes might be the same length as the third metacarpal, or maybe even a little bit longer. But because of where it is anchored down here in where the carpals are, it's a little bit lower. So it's either at the same height or a tad lower. So typically you end up getting an arch. And so if we overlay this thing here, we're going to kind of see it's like, yeah, they should have brought that down a little bit because the middle finger should be up a little bit higher. So why were they not able to do that? And I think, and again, if we look at an actual human X-ray and overlay it, we'll kind of see the same thing that's going on there. And again, this is that kind of arc that surgeons would be looking for to see that your hand is kind of correctly spaced. So they have a little bit of a problem there. Now, what might be the issue that's going on? We're going to be doing a deep dive into how the actuation is done. And my suspicion is that the motor units that they have in here for being able to do what's the finger flexion are of a certain length. And that length comes down here and gets very close to the CMC joint of the thumb, and they can't bring it down anymore. So it probably forced them to make a little bit higher. So they're going to have to make some decisions of either, and actually, I think it would recommend bringing that CMC joint down anyway, or they have to make that a little bit smaller. But we're going to be getting in the details of that. And I don't want to jump ahead too much, but I suspect that might be part of the reason. Okay, so pretty good grip. But I showed this frame here. This is the transition to the glove. So you can kind of see how it fits into the glove. And we're going to see that they definitely designed this with the idea of a glove going over it and are going to take advantage of the skeletal structure they have to make sure that when they fit a glove on it, it works a lot better. So um, one of the things of the glove is the finger lengths are all the same. So it's probably a challenge to actually find one the same length. I'm not sure if they made this themselves or got one sort of off the shelf, in which case it kind of stretch things a little bit, because I suspect in a couple of the images, it looks like, because we know the pinky is much longer, I think it does get stretched out a little bit. But as we begin to look at these things, I want to make sure everyone is clear on the notations that I'm going to be using. So this is a notation I've done before using the Tesla bot hand as an example. You've probably seen this before. Pause the video and study it if you want. But we talk about on the fingers the names of your knuckles, which are distantly, dip, pip, and MCP. So the knuckle down by your palm is MCP, and then going on up your fingers. And then you have the phalanges, which is the proximal, the middle, and the distal that are out there. So everyone's kind of familiar with this terminology. And the CMC joint is the joint down here on the thumb. Okay, so with that in mind, and we're going to go ahead and try to figure out how do they do the actuation. First thing, identify where are the pip and dip joints on this. Fairly easy to do, right? I think everyone knows where it is. So you see these little black dots, which are kind of making what looks like an axis through here. I'm going to label them, and if you can't notice them already, that's where they are. So we have the dip joint here and the pip joint there in blue, the dip is in green, and that's the axis. Now, imagine for a second, if you're not using tendons, what's one way to get these joints to rotate? What's one possible way?
Rotary motor, small rotary motor, or tendon.
Yeah, yeah. Well, if it's not a tendon, what we could do is you could imagine, why not put a small rotary motor in there? And there are some examples of companies doing exactly that, except it really is a very small rotary motor, and it's very, very difficult to get the torque that you need. It also gets very big. But if you think about it, that's exactly what all the robot arms are doing. On the knees and the elbows, up at the shoulders, they're putting the motors right there where the joints are going to be. So the motor forms the joint and they do everything. And that works well for a much larger kind of mechanism like an arm. But when you start scaling it down, it becomes harder and harder to be able to do that, to get the torque density you need so you can have really good motion there. So you're going to have to take another approach, and we're going to try to understand exactly how that's done. Now, down here is where is the MCP joint, and you have 2 degrees of freedom down here. So unlike going up in the pip and the dip, they are simple pin joints there. There's actually 2 degrees of freedom here. And again, I want everyone to look at this and try to figure out, where exactly is the abduction and the flexion. So the flexion is, of course, the movement when you close your grip. The abduction is when you splay your hands out. And if you look at it, I think it should be pretty obvious. I'm going to reveal one, and then we'll look at the others and see how they kind of stack up. So this is your flexion. So that is in basically the same direction as the flexion on the pip and the dip. So you pretty much have 3 kind of flexion joints going on at the same time there down at the MCP. What's rather interesting is that the abduction in this case is happening between those flexions. That's unusual. On all the other robot hands, usually the abduction comes first, then comes the first flexion, then the pip, and then the dip. And so in this case, as we can see, it's down just underneath it. Ideally, you want them to line up. You would like to kind of make a spherical joint there, but there's mechanical reasons and packaging reasons that sometimes makes that very difficult to accomplish. So it's a type of cardon joint, but with an offset. I mean, you can make these things that they intersect, but again, it may be that it's very complicated to pull that trick off. So the result is that you've got a little bit of an offset. Usually the offset is that the abduction is down here a little bit lower. So if we look at where Tesla did it, we can see where the abduction is, these green arrows that I'm kind of pointing at here around those dots. It's below where we're having the flexion at the MCP joint, and then you see that. So normally you have all 3 flexions together. This is a little bit different. Doesn't really make a big deal from controls or anything like that. The math is not that much harder to be able to figure out. Okay, so that's sort of what we're seeing, and we want to proceed ahead and figure out how do they actually go ahead and get these things to move. Okay, so looking at here, again, using the overall terminology that we've had already, I want to make sure everyone is clear on what is the distal phalange. That's the very tip of your finger. The middle phalange is just called the middle, and the very first one is called the proximal phalange. Okay, so those are the three segments that make up your fingertips. And of course, we just talked about the joints between the dip and the pip, and then down here the MCP. Okay, so now I've highlighted the distal phalange, uh, including on your thumb. And the one thing you'll notice up here is that these fingertips, they appear to really just be solid blocks of metal. They're completely inert. There does not seem to be anything inside of them. There's no motor in there that we can see. And there's just this joint down here. When we come down here at the thumb, we're going to see it's done a little bit differently. The thumb distal phalange actually has a motor built in here. And we will, but I'm going to address the thumb kind of on its own, in its own merit, because it's a little bit different. So that's the first part of these segments. Now, the next thing that we need to have is that at these joints, we have what I call an IP reducer. So with the middle phalange, we're going to see it's made up of several segments here. The top segment is this IP reducer, which is going to be taking the output for the motor. So my suspicion is the motors are actually form the phalange themselves. So the axis of the motors is along the flange, and it's rotating in the wrong direction. So it's has to be rotated 90 degrees in order for us to be able to rotate along the IP direction. So that's why I call it the IP reducer. It basically is doing two things. It's changing the direction of rotation, and it's also probably got a gear ratio in there of some sort. So you'll see that they happen in all these different sections, and they look like a T that fits inside of the Y formed by like the distal phalange. And what we're going to see is some of these other segments here. Now, just below there, I believe is what I would call the phalangeal motor, that they probably make up two of these segments in there. Not sure why there's two segments in there. It could be one part of it is where the control board is, and another part is the motor. But basically, it's all going to be in there. And then we have another rather inert part, which I call like the IP joint. So it's like this little segment here, which again forms kind of a Y shape or yoke, very much like the distal phalange. That's just the part that is the connecting unit between the IP joint and then the following phalange that you're going to have in there. Now, and then of course we see the IP reducer that's down here that's switched around. So as you'll see, what ends up happening is that there's usually a motor underneath one phalange carrying the other one and rotating the one above it. But in this case, it's flipped around, and that is carrying itself down in here because you have 2 degrees of freedom. That's the trick that has to be done there. And then finally, there's this section here, which looks like some kind of motor interconnect, because we have 2 motors here, and we need to do something to connect those sections together. And normally the base part of these motors, as we can see, like up here in some other sections, is that you have the IP joint that would stick underneath it. So you get the motor, and then above it, you're going to have the reducer for the output, and then underneath it, the thing that kind of connects it to the segment below it. And now in this case, that's connection is done by flipping it around for the proximal phalange, because that's the longest phalange in your finger.
Couple of question maybe
Sure.
so to understand firstly, what kind of motor do you use? You said the rotary motor, but
It's a rotary motor. It's a very small, compact rotary motor. And I think it's a brushless motor. They mentioned something about it. So it has pretty high torque, and because it's fitting in your finger like that, they can make that motor a little bit bigger, and the diameter a bit bigger. So the length and the diameter can be a lot bigger than if you just try sticking it directly in the joint. So you put it directly in the joint, you can have really big knuckles, and it's going to be very, very difficult. So they're like, wait a minute, we can make this a bigger, more powerful one, and it actually forms the structure of the finger now. You're not having something else trying to connect it together. So it really, it's the clever way. It seems like the most obvious way to do it. If I was going to be building these things, I would have imagined doing that. It's just that you look around and say, oh, you can't make a motor that powerful. So everyone gives up.
do you think it was made in house or off shelf? Because the way of design it, you think you have to choose the motor and then build around it.
Well,
Or you
they're
have
experts on motors. They've been doing this for about 6 years now, building very small, compact, high torque motors, and for robotics. And so they then say, hey, now that we have this, let's go ahead and see if we can make a hand out of it. So yeah, it's all in house, and that's what's really quite interesting about what they're doing. Okay, now there is some information that you can get on their website here, which is the brochure, and that gives some rather interesting background. And even though, I mean, you can give this to chat to translate it into Chinese. But for the most part, you can make a pretty good guess of what everything means. And they also have like some spec sheets in here, which will kind of come back, give us an idea of range of motion, torque output, and everything else. And as a result of that, there was also a couple of images in here that were helpful because we weren't able to see the top of the hand in the video. And I was hoping to see a little bit more of the top of the hand, but there's a couple of images here that really help us understand what's going on. So this one image I clipped out, which gives us a really nice side view of it. And I put this center line right through here, this black center line, which is pretty much the axis of rotation that that motor is going to be on. And if you look down here, this is where the rotation of one of the IP joints is. And you'll see that there's an offset between the two. And that's sort of a hint on how they might be taking the rotation along the black direction and creating rotation in the red direction here. So how would they do that? Well, there's two ways that you can change the direction of rotation. One is you can use a worm gear, which is we see here on the left side, or you can use a bevel gear. And they have their pros and cons. And if you see here, if you look at the worm gear, you can see that where the center line is up there, and you can see there's an offset on the axis of rotation between the two. Whereas with a bevel, you can actually line them up. There is no offset between those two rotations. Those axes actually intersect. The problem is this gear here isn't up in the middle. It kind of has to be shifted down sideways. So by looking from the outside, we can kind of guess whether they did it or not. So let's say, well, maybe they used a bevel gear. Would that make more sense to go ahead and do something like that? And I think not, for this reason. And that is, from this image here, again, if we look at the yolks here, and I picked the color Y for yolk for a couple of reasons, the yellow for that, and also egg yolks. And then you'll see the T colored section in here, which forms that little T, which is the output. That's the IP reducer. And you'll notice that they're symmetric on both sides. And if you had an output that was a bevel gear, that would mean that the gear is kind of pushing over to one side or the other. And you would suspect that this would not be symmetric, that one side would be thinner than the other. And you do see this a lot in robotics when they do that, that you will see a mechanism like that, a yoke type of mechanism, and you'll notice it's much thicker on one side and really thin on the other. And a lot of times it's for that reason, is because all the mechanics has to go somewhere. And so it's basically the vertical segment of the T, the upside down T that we see there, which is where we would have to house it. And I just don't see it fitting in there. I really don't. So what I have done is said, like, imagine taking this worm gear and trying to reduce it down into there. Does it kind of fit in there? Line it up, and whoops, and we can kind of look at it this way. So now, remember, you can change the size of that output gear to be anything. It can be bigger or smaller. If you make it a little bit smaller, that means the worm gear would be a little bit bigger. So if anyone's wondering, oh, mechanically that's kind of crazy. The worm gear looks too small. Shouldn't it be bigger? Yeah, potentially. And I think there's still enough room to be able to seat it on both ends, because you want to make sure that the other opposite end of the worm gear is going into some sort of small bearing, just so it's able to not flex and everything else. It's a tight fit. But somehow they're doing it, and unless they're going with something else. Those are the two possible ways, and that's why I think it might be a worm gear that's going on in there. Okay, now that takes care of kind of how the IP joints are going. Now we want to focus down here on the MCP, because we have these 2 degrees of freedom. And we can sort of see that we have a motor segment down here and an output. And this IP output is just a little bit different than the others. It had to be designed different because it is doing something different. And if we look down here on what appears to be the cardan joint, a type of cardan joint, we'll see this big black section here that actually goes all the way up in here. So I want you to think of this, and there seems to be like a lever arm popping out here, which is going to be important in a minute. And we can see through here, there's kind of this black axis that this is tied into. The brass colored stuff around here, this is like flexi cable that they do to route all of the power that's going in here in a very clever way. That's the cabling. It's not structure. It just happens to be the color. That makes everything a bit confusing, but they're wrapping it around it to make sure it's able to handle the flexing that's going to be going on. Okay, so if we look at that a little bit closer, we can begin to see that up at the top here, I've highlighted what is the PIP joint in blue. And now down here, the yellow joint, this is what is going to be the abduction that's going on. And you notice those two arrows are kind of perpendicular to each other. So and what that means is the lower motor section is the one that's responsible for abduction, not for flexion. Okay. So the flexion is below it. And we're going to understand why they decided to change the order in just a second here. But in order to do that, that means that lower motor section has to be rotated. The output is 90 degrees to the blue one. So that means those two motor sections, rather than being aligned exactly the same, they're rotated to make sure the output of the other kind of does it right. And we can kind of tell that if you look here on the side view of the hand, you can see where that brass cabling goes up on the finger. So if you look at the medial joint, the one in the middle, you can see the kind of the brass colored cabling there. And then you see it's at the top of the proximal, but you can't see it on the bottom part of the lower one. That's because it's rotated 90 degrees out of your field of view. So it's on the top of the knuckle. So we haven't seen a good picture of that, but I'm pretty sure that same kind of routing that they do, the cabling, is on the back side, which shows that, yeah, they had to take the motor and rotate it. And that's what happens with that interconnect between the two, is that the two motors snap in 90 degrees to one another to create the output. Now, this side view is going to be important for a couple other reasons, is that we're going to be able to get a glimpse not only at how the mounting of the thumb is when we get to the thumb, but to understand a little bit of how they are actuating this whole thing. And what we're going to do is focus in now at how are they doing the flexion. So we can see how they're doing the abduction. The abduction is being done by the lower motor in the proximal phalange. But how are they accomplishing the flexion? Because it's not clear. There's no kind of simple sort of motor in there. It seems like an absence of anything in there. And the key is focusing on these two black screws in the back, these screw heads that I've circled in red to give you an idea. And the hint is, it tells us that what they probably did is they built a small 4-bar linkage in here, a parallelogram 4-bar linkage, where the flexure motor is down here somewhere, and you have sticking out here, which would be a lever arm, with a connecting one to the other lever arm. And I was telling you about that black piece that's up there. That's one big piece, and which has a lever that sticks out over there. Now, this is just from the video. If we go ahead and look back at the brochure, where we can see the top view, we begin to see what looks like, oh, wait a minute. Yeah, we see some weird things happening at the top of the wrist. And you can see one of them in sort of the extended position, and one of them where it's completely retracted. So right now, the index finger that's up is kind of in a back position, and the other hands that are clenched, you can kind of see them that they move forward. So we don't have any video of that movement. We only have like this still image and the other one. Mhm.
Can I ask a question? So this is the image show the 4-bar links mechanism in this image. We can
Yeah,
see it.
well, you can kind of see it. It's a little bit tricky in the knuckles. Here's a better image of it right there. Okay, so we've seen this picture already. Look back here on the top of the knuckle, and now you can see it better. So here's the knuckle, and in here in the red part is something that we can't see. So back behind there is a pivot point, and we can sort of see what looks like a linkage mechanism going between here and there. And we have a rotation in green, another rotation point in blue, and another one here in purple. And if you look at this, don't be thrown off by the fact that this has kind of a dog leg in there. All that matters is the geometry between them. Okay. So we have these points. So now you can see what makes the linkage. And when they rotate it down here, they can get, and that way they could have like a big output shaft that just doesn't fit up there. It was just going to get in the way, and they can move it down there to get that kind of movement. So that's the trick. This is very common in robotics. A lot of robot arms, especially in the old days when they couldn't get the motors to be strong enough, and they had to put them down in the base to make them really big and bulky. That was how they did it, is they had a parallelogram 4-bar linkage that would get the upper arm to move back and forth. So this is very common. And the fact that it's a parallelogram means the input is equal to the output. So the movement of the red axis will cause the exact same amount of movement in the purple.
But you say then it's a space this in the previous image. There's nothing in the space. It's kind of void. Why they opted this decision of making 4-bar links mechanism and doing something maybe straightforward?
Yeah, I think it just comes down to it was really difficult to put it in there. So remember that sort of the IP reducer I was talking about? It might be that the reducer they had to put in there was much bigger and it was so oversized, they just really couldn't get it. So they had to use this remote actuation strategy. If they could have got away without it, I am sure they would have, but they just realized that, mm, there's no other way to do it remotely. And I think I understand part of the reason why. And this is also going to explain why the flexion comes first and not the abduction, because almost everyone does it the other way around. And that is, it kind of comes down to a packaging thing, is that they have two size motors. They have the motors that are in the fingers, and they have some motors that fit here in the palm, because in the palm, you've got more thickness. You can put something a little bit bigger, a bit stronger in there if you want. So they've gone ahead, and I believe if you look at that, you'll see the palm is a little bit thicker. And I've been able to confirm it by looking again at their brochure. So even though this is in Chinese, it's really not that hard from context to figure out what's being talked about here. Because if I blow it up a little bit, there's this point here that's referring to the torque output for the IP and the MCP joint. And you'll see the IP joints, the torque is 0.3 Newton meters. And for the MCP, it is 1 Newton meter. In other words, it's 3 times more powerful. And the only way they're doing it is they have a motor that's 3 times the size. So it's a little bit bigger to be able to do it. So they couldn't fit it in there. Now, why do they do that? One of these, yeah, the fingertip force there. Here, it seems like the brochure might be out of date because they said 20 in the video, but this is what they're able to carry, the carrying load. So they can do up to 20 kilograms. Now, I'm going to try to get my hand up there. So if I'm going to be carrying something heavy, I'm going to be curling my hand around like that. And actually what ends up happening is it's the proximal phalange, which is carrying the whole load. The other 2 fingers, the only reason they're there is to make sure it doesn't slide off. But they don't actually have to carry this mass. What has to get carried, what is carrying the mass is basically my fingers right in here, right? That, yeah, it's not the middle one, but basically this one right here. The very first one is where that load is. When you go and grip something, that's there. So that means most of the power needs to be in your knuckles. So if you can generate more flexion there, that's the most, and that's why the flexion had to come first. Because imagine they said, "Oh, what we're going to do is we're going to use the motors in our palm for the abduction." Well, you don't need abduction. You don't need any strength in the abduction. They're weaklings. Okay, what you needed is here. And so if you are using now that lower motor in the phalange for being able to do flexion, you're going to be too weak. So the way you get the strength is you say, we're going to flip it around. I'm going to do it that way. Now it's a little bit bigger and it became a bit more complicated to be able to get it. So they had to use that remote activation strategy. I mean, who knows? Maybe eventually they get around and are able to improve it.
It makes sense now. That's the reason that the abduction actuation come first and then flexion at the
Yes.
end. Do you
Yes.
think other companies doing that? Like their strategy when you compare it to other people?
Depending upon how they do it, that makes sense. I mean, I like that approach is that, this is where the power needs to be. So we're going to have to do that directly. And maybe the abduction can come second and we can find some other way to actuate it. So that's a pretty good idea. Now, the thing is I sort of hinted before, the reason why the index finger is up so high is because those motors are so big. They were kind of forced to put it up a little bit higher because it then got in the way of the packaging that they need to do for the thumb. So again, if we kind of look here at what's going on in the activation between the thumb and the normal fingers, you'll see the thumb is reversed. So the distal tip of the thumb actually has a motor in there, and the IP reducer is below it, which means each phalange is carrying itself. It's carrying its own weight. Whereas over here on the fingers themselves, no, the one below is carrying the weight. So we can see, that Y yoke is down below on that. So that's one thing we can look at the thumb. And another, we can sort of see here. And again, if you look at the packaging, everything I have there, I think it just ran out of room. That's why that one's a little bit higher. So we get a nice close up of how the thumb is able to move. And we're going to look a little bit closer in here at what's going on. And one of them is going to notice how it's mounted. It's really mounted askew, which will become clear in some of the other pictures at the CMC joint for, I think, pretty good reasons. And if you also look on here, and you may not have noticed on the others, I just want to go back to these fingertips. We never really talked about what's going on out here. Behind each of these things, you can actually see a fingertip. I should say a fingernail, not the tip, but there's actually hint of a fingernail that's got a little bit of space or separation in there. So I think they're planning on designing some sort of gloves that really fit around there because having a fingernail is really good. We'll also notice there seems to be this big void on those tips. It's like, what's that all about? And I think it's because they want to have actually a little bit of pulp in there. So when the glove goes in there, they probably actually have something in there to make it a little bit soft to fill it out with material. So it's not your normal glove that just is very thin. They're going to have some pulpy material that goes in there, fits on it really well, makes it really tight. And but you're going to have a fingernail kind of built in that will allow you to dig into things a little bit better. Okay, so I outlined what is definitely the fingernail of the thumb or the thumbnail, and you can see that's pretty pronounced. That's not there by mistake. They're really thinking about it, even with a glove that's going to be going on over it. Okay, so here's another view of how everything is sort of mounted into the palm. Looks a little bit interesting in how they put it in there, and now we can see the actual joints. So again, 20 degrees of freedom and 5 fingers. That means 4 per finger. So the thumb doesn't get any extra here. Sometimes you could add another degree of freedom to the CMC joint, and that's how you get your 21 degree of freedom. It's nice to have 3 degrees of freedom down there to get full mobility of the thumb, but they're doing a few things to kind of help reduce the need for that, even though they still need a little bit more mobility. But we can see the 2 green axes up here, and these are your normal flexion of the thumb. And again, they're done by the flange itself. It kind of carries itself, and they're all in order. So we have a motor up the distal, we have a motor in the middle, and now we have another one down here on what would be kind of the proximal of the thumb. And you can see it's rotated 90 degrees because its output is red. And sure enough, we can now see the exposed cabling here that we didn't see up here. I think if we go back to these here, we can kind of see they're doing their cabling almost the same way. And then we come on here. So we can see, sure enough, it's rotated 90 degrees. And then we see this blue in here. And if you look at the angle of that blue, it's like, that's a weird angle. Why are they mounting it that way? And also if you it's kind of hard to tell. I've looked at other images. I'm not convinced that the blue and the red are exactly perpendicular to each other. I think they're off a little bit, and that's intentional. So, um, most of our joints, like our IP joints, we can consider, and I'm just going to stop sharing for a second here to get into that, and probably makes it a little bit easier right here. Okay, did I stop sharing? I'm trying to think if I did.
Next to the red, next to it.
Oh, there it is. Okay, yeah. Okay, so what's so typically all our fingers are almost like a ball and socket joint, but not quite. So our out here, our IP joints, for all intents and purposes, they're a hinge mechanism that has only one axis of rotation because there's all these ligaments and everything else that make sure it can really only go that way. Down here at our MCP joint, it's also a ball and socket joint, but we really only have 2 degrees of freedom. Yeah, you might have a third one in there, but don't try it because the ligaments are trying really hard to make sure you cannot exercise that. If we look at our shoulders and our hips, they're real ball and sockets, and we're able to get the full 3 degrees of freedom out of that thing. So there's a lot of things that restrict it. Now, down here, basically our thumb is just the same as any other finger, but evolution kind of forced it on down there and made a couple modifications. So the CMC joint down here is kind of the equivalent of what's going on up here, except it has a bit more mobility than you do up here. And a lot of it is because we need the thumb to be able to come around and do everything. And you can kind of think of it as a ball and socket joint. But the thing is the ligaments and the tendons and everything that kind of comes around there to actuate it, they aren't all like orthogonal to each other. So to say that you have a pure rotation about this axis and then another one about that way and everything else is you get more of what they call kind of the circumduction, that the movements you have results in many cases the movement of more than one of these things as opposed to just a single one. So usually when we put a motor on here, we think of, oh, I got a motor that just rotates it this way. And the same here. One makes it go this way, one makes it go that way, and that's very clear. It's a bit more complicated than you have down here. So, one of the things is like you really can't rotate your thumb about there, even though there was like recently a robot hand that showed it could rotate. It's very hard for you to do that in any position. But if you actually look at your movement, the tip of your thumb will kind of rotate a little bit as these others are happening. That's what we refer to as really kind of that circumduction. So you have a certain amount of movement of it, but let's say not quite the full degrees of freedom that you would think of that when you have a spherical joint. So it's technically 3 degrees of freedom down there, but it's almost like 2.5 in a way. It's not quite there. So sometimes what you can do to emulate that is if you just think about lining your axes up in a particular way, they make it very close to doing it. And it may be eventually that someone thinks about, wait a minute, why don't we make a joint that rather than rotates in a particular way, kind of wobbles around or processes that as you do it does something else. And you might get a bit closer doing it. So you don't have to put a third motor in there. And that's what I think they are attempting to do is they're saying, hey, in order to get this thing to work right, we want to go ahead and find some way that we mount it on there that kind of gives us that movement. And that's a good thought process. I like the way they go on because otherwise you're looking at that and say, why is the blue axis that way? It seems like it would fit in a little bit nicer if they turned it around a bit different. Another thing this has opened up is that because this palm is not as crowded as everyone else's, it's not as thick. And they're also able to get some shape to the palm that's a bit more like a human hand. So a human hand, we already have kind of a cup in our palm here. That makes it very easy for us to balance items in there. And also, the one thing they can't do is they can't scrunch the palm together. But a lot of times we would like that for catching certain things. But then there's other activities we would like a flat palm. So if we're carrying a tray or something like that, so that means they've designed it to be kind of like a flat palm, but not overly flat because there are some palms out there just so flat they are missing that. So they're trying to capture that without actually having to have the deformation, which ideally we would all like to have something like that if we could. Okay, any questions about the thumb?
I think that the biggest question for me about this company is different design of the hand. When they start the design process, I think that's in house, so they have everything. But when they came up with a different design that you have to see already, there's already many hands. But
Yes.
what is the most yeah, maybe critical way of the let's start this hand and you see this hand is different than the hand. So what is the maybe differentiator between each of these designs? Like
Oh, I think the big differentiation, and they point that out a little bit, is that because they have no couple joints, they have full control of everything, absolute full control. And because of that, the sim to real gap lessens. You don't have the problems with tendons. Tendons are just very difficult things to do, to maintain, to get control of, and everything else. Um, but they have some advantages potentially on giving, really good strength. So attempts to do this before resulted in a hand that was too weak was all very nice. But it's just this wasn't strong enough. And this is an exciting direction and could be the future of a lot of hands. Again, like I said, others have attempted to do the same thing mechanically, but with more of a mechanical tendon as opposed to an actual tendon where the motors are still kind of remote and through remote activation, basically 4-bar linkages connected to other 4-bar linkages that allow you to get the finger to move. And this allows you to make it a lot lighter, seems to be reasonably robust. I mean, we could see they were banging it up pretty well and it came back. They also talked about in the brochure, like the number of cycles these things have gone through. It's gone through some pretty rigorous testing. So it's a serious hand that I'm pretty sure they're thinking of selling because there's a lot of robot companies out there that are trying to figure out, are we trying to be a humanoid robot company or a hand company? We have to be the best at all, or do we just have to have a good enough hand? And this might be make it a lot easier for people to say, I just don't want to focus the energy because the hand is going to be half of the engineering. Tesla's already said that. I mean, it's like more than half of the engineering is going into the hand as opposed to everything else. So it's a complex problem, and it would be kind of nice if someone else solves it for you, and they just get it
maybe
off the shelf. Mhm.
ask a question about the glove because this
Yes,
the glove I think make a lot of things if it's off shelf or maybe they did it and it's specifically for this design to I
they,
think to complement the skeleton that's hard and soft problem.
yes, yes, yes. So they having a glove sort of makes sense. Not only does it soften it, but it does kind of protect some things. And it's possible that all the sensors, because they don't have any sensors in here except the encoders for the motor positions, which you can get some force feedback and obviously good position control from that. But as far as tactile, it's it's not there, which I think is a good idea because there's a lot of data gloves that are starting to have tactile built into them. That means all your cable routing and stuff like that, you don't worry about in your skeleton. So it's like, I'm not worrying about that. It's in the glove. And you just pop the glove on there and you have it. And it may be that there's some other manufacturers that are solving that problem. So you just say, I'll let them solve it. They're the experts on that. I'm going to solve this other thing. And then we just integrate it together.
I want to ask you a few question here. You saw figure hand, I think. The
Mhm.
figure hand is rigid. Like you don't have
Yes.
maybe they and also we speak about Dux Robotics, Tom. We had him in the podcast and his philosophy to use soft hand. They
Mhm.
have tendon. So how do you see these different approaches? Who could be the winner in that case if we speak
It
about the
could be that
humanoid?
there's many winners. Um, I I had the opportunity to actually hold on to Tom's hand. You can in the edit show that, and it's very soft. You know, it doesn't hurt. It's not mechanical. And if I was in more of a healthcare setting, that's the hand that I would want to have coming over and like taking my pulse or doing anything else. So in those kind of settings, it may be good. In a more industrial setting, things are just rigid or really rugged. You need something very robust, and you don't care about something that's going to give you a good handshake. You care about something that's not going to break for 3 years. So depending upon the applications, there will be probably the better hand design for those. Sometimes you don't need 20 degrees of freedom. 16 may be more than enough to do everything you have to do in those tasks because they're very simple tasks that don't require threading a needle or doing anything complicated. So I think that's what's going to happen is that everyone's going to find that they have some designs that are good enough. The other thing sometimes is it may not just be as easy as buying someone's hand and connecting it to your bot. There's kind of like an integration with your ecosystem. And a lot of times, if you've done a lot of training with a particular hand and you change to a different hand, suddenly burp, your data set is like almost thrown out. You have to start from scratch. So in many cases, you have to be cognizant of that. And again, are you an arm plus a hand, or do you have a forearm strategy? So as you saw with Alex, that their hand strategy was that it's really built into the forearm, just like Tesla is, where the wrist joints and everything are kind of part of it. So you can't separate the hand and just give it to someone else. You would have to actually provide the whole forearm. So there's going to be a lot of these different strategies. I'm not like cheerleading for one or another. I'm cheerleading for all of them because I don't know what is the correct approach yet. And I'm so glad there are people looking in a different direction because they may actually come up with something that really is a great design that everyone else eventually is going to copy.
I like that. I like your answer. I think you're right. There's be different winner. But I want to ask you what maybe other different philosophy or strategy to design the hand that you think could be there's a room to do this better. Do you think it's about packaging? Do you think about the actuation? Where do you think maybe something's still missing and that maybe explore something else? Because it seems that every once in a while there's something some improvement hand, like the way the
Yes.
flexion is designed, maybe the packaging, maybe the actuation. So do you think what is the most difficult thing or maybe still a challenge to make this hand if we wish to be exact as human or more beyond the human, as Tom already says, think about beyond the human anatomy and the hand. Yeah.
Yes. Everything really comes down to actuation. And whether you have to have remote actuation. So anyone that comes up with a better actuator, be it really good artificial muscle or something like that, that's going to be key because it all comes down to torque density and being able to fit everything where it needs to be, and at the same time, the amount of sensing you need to have in your hand. What kind of touch sensing and other kind of feedback, and is that something you can integrate directly into your actuation strategy, or is that something separate? And it's like, wow, one more thing I have to kind of build on top of it, or can I come up with something that gives me almost 2 for 1? I mean, motors give you a little bit of that in that they can give you force feedback, which is like pseudo touch. It's not exactly the same as touch. I've seen some people mislabel it as like, "Oh, a robot has, like, touch sensing." It's like, "No, you came down and you get, like, force feedback, and you're saying that's touch?" It's very different than going through and knowing exactly what's on there. Now, Tom Zhang actually has a very interesting approach, which he showed me because he has so many different tendons in there that when you touch his finger in a particular direction, he does have like a force feedback, but he can tell where the force feedback is coming from. So if you just have like an actuator here and you touch the tip, I can say, oh, there's some resistance there, but I can't tell if it's coming from the left, the right, or where it's actually coming from. Because Tom has got so many tendons in there, certain tendons react a different way. He's almost got touch sensing in there as a result of his actuation strategy. So again, there are some clever ways of getting a 2 for 1, and we'll have Tom back on here. He definitely has some more things to talk about since we last chatted with him, but he just moved to Austin, so he's a bit busy. Anyway, kind of proceeding ahead here. This is starting to show us the gestures, and I don't know if it's by happenstance, is because all these other researchers are kind of uncovering the same thing, or if it's because us talking about this. But there's different ways of scoring how well a hand works, and one of them is called a Kapuni score, which comes out of hand surgery. It's a hand surgeon is well aware of looking at the kind of the dexterity or what they call opposition that you have. So it comes down to how many different points you can take your thumb and touch on your finger. So there's like evidently there's a 0 position here. There's like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, something like that. So this is trying to do that opposition. And several of the videos coming out now are one of them explicitly showed that that's the Kapuni. This one is kind of doing the same gestures as well as some of the others to kind of prove it, but it's going a bit further because you notice that on my middle fingers, I only touch the tips. They're going down like that. So it's almost like they're trying to go for an unheard of Kapuni score of 20 or something like that by getting more different positions. So when it ran along there, it did that. Now, the thing is that while they can kind of get that, it's not quite the full score because you'll see that it's the fingertips kind of come together like that. To really do it, you should be forming the proper O. So that's again where like with the extra mobility of your thumb, that the fact that this joint is down a little bit deeper allows it to swing way out, allows us to kind of come together and form an O with our tip, as opposed to coming in perpendicular the way they are. So it looks like, oh, they get a 10 on there, and probably the hand surgeon will go, no, that's not quite, it's not quite there. But it's good, pretty good dexterity because many others can't get there at all. The other thing I want you to notice, and I think I end up, okay, so this is the Kapuni score, how you're able to go through and find all the different places. You start in the outer, then the tips here, and then you basically go for the creases. Now, that same one, you can actually see the fingernail right there. So you see how it kind of popped there. Get a little bit extra stretched, I think, because maybe this glove actually has a shorter pinky. So, and you can also see the thumbnail up there a little bit. So that was rather interesting to see that, yeah, it's coming through. And I can imagine a special cutout on the glove they put in there to actually expose it and still let it slip in there. But I think this is just a normal glove that you use for jogging in cold weather or
I still do remember exactly the reason of the nail.
oh, well, there's several reasons for a fingernail. One is it allows us to pick up things like needles and coins because you really need that little pincher to be able to do it, but it also actually provides stability to, the flesh underneath. So where your pulp is, if you were to remove your fingernail, then you actually lose a lot of stability. Everything around there kind of slides around. So even underneath, it helps provide a little bit of support. So the fingernail is very important for that. But obviously the sharpness that you'd be able to have on there. So it's sort of nice that it's one of the few hands that I've looked at that I've seen that they're actually thinking about that as opposed to just these round tips that don't seem to do any value whatsoever. So that is definitely more biomimetic and again, more like the human hand. Okay, so definitely large range of abduction movement, which we can see. I believe it's 60 degrees total, plus or minus 30 degrees, which is probably more than we can do. And then again, with the fully actuated rotary joints, they can get all of the gestures that you want. So one of the gestures that we want to have is that when we close our fingers, we don't want to have this clawing motion. And this is what a single tendon gripper will do. As you start to close it, everything will come down and you claw. What you'd like to do is have your fingers come down straight and then be able to close them. And in order to do that, you need to have a second tendon, which is your extensor, which is the one that will open your fingers back up. And through process of antagonism, you can kind of get them to move. Now, even though we have the antagonism, it's really hard for me to individually control the different IP joints. The only way I can get IP joints in certain positions is if I give some resistance that might kind of force them into an unnatural position based on what I'm usually doing. They can control each one of them individually, so they can do gestures that we can't. It can do all of ours without a doubt, but also ones we cannot do. And actually, Gustav Anderson pointed this out to me that this will be able to play the piano better because we have a multitude of tendons and ligaments in our fingers that give us incredible control. Not all of them are in the forearms. So the ones that give us strength are in the forearm, but the ones that give us the fine control are actually our intrinsics up here. So for playing the piano, you'd be thinking of getting your fingers a certain position, but this movement of your finger up and down like that, that's done by your intrinsics in your hand that is not controlled by something over here. So having two tendons, I mean, they may talk about the Tesla bot being able to play the piano, but it won't be able to play it as well as a human hand, nor as well as this, because it won't have that kind of being able to drop your finger down like that. Sure, it'll be able to hit the notes. It'll be play better than I will, that's for sure.
How we can do that, that design that we have in our hands, as you explain now in
You
this
would
hand.
have to add more because our fingers really have, I think it's like 3 flexures that go there's multiple tendons that come in here that allow the flexion, one for coming back, and there's a bunch of these intrinsics because you have the same number of muscles in your hand as you do in your forearm for controlling your hand. We think of that, but the one the forearms are stronger. So from the standpoint of strength, there's more, but the actual number is the same between the two. So this idea that they're mostly down there, it's like, no, 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 they're not mostly. That fine dexterous motor control is as a result of intrinsic muscles up here. That's very hard to do. You do something like this, oh, I'm direct drive because that's the whole point of these intrinsics is for me to be able to control one of those IP joints to a specific way that's very, very hard to do. Extremely hard to be able to do with tendons, but with this, man, real easy. Whatever you want to do, just tell me. So again, fully articulated rotary joints. We can see that they can do the straight finger there, no problem, as well as moving an individual distal joint. And this is the key. Simple kinematics, which means minimal sim to real gap. Absolutely, I believe, I didn't even have to see that statement to agree with them because I already knew, wait a minute, you get rid of all those problems because tendons are going to be very difficult. Again, you want to get a plinking kind of movement like that with my finger. The number of tendons that you need to be able to move and coordinate gets very complicated to figure out what you would have to do that. This is very easy. And the other thing is because the tendons don't have individual control at a particular joint, if I'm getting certain resistance somewhere and I want to maintain my finger in a certain position, I don't know how to exactly do that with a tendon. It's really hard to say this. It's in order to keep, but this way with the motor, it's like just hold that position, just increase the torque. I want to keep that thing at 30 degrees and just do whatever. It's very, very easy. That means sim to real becomes much easier for this to do more dexterous tasks. And it might even do a better job without even having to have touch sensing. So it could be that if you take a tendon-based one, you have to put touch sensing in there and do a bunch of other wild tricks to be able to kind of get the control that you want. This might be able to do it more straightforward. So from the standpoint, if you want to have a hand working really quickly, sim to real, boom, I would use this, this approach. Again, brushless servo, so we know the kind of motors they have in there. Um, Standard, I think just about everything is brushless because lower maintenance as a result, and very high communication rate bandwidth between them. And again, we could see the way those cables were put around there. Man, that just looked like craftsmanship, the way they put those flexi cables around there. Really well thought out. Um, yeah, so that's again, it looks very human-like. The 20 output encoders and 20 input encoders, it basically means they have encoders on the motor, the output shaft, the motor, and also on the reducers. So they make sure they sync up. It's kind of important because when you lose power or turn out, you can lose a relationship between the two. So you want to know exactly where's my finger, not based on what the output is, but what that is. And then once that relationship is reestablished, then it's much easier to control. Uh, Again, it looks very good. Because of the arching that they have there. If you kind of look at that fist and look at your own when you make kind of a similar kind of fist, it looks very close because you see how it slopes down. Many other robot ones, you look at that and they're very straight. They're very horizontal with everything else. They just don't look natural. So that's much closer. The only thing that I'll kind of point out when we get into some of the gestures that they do, a few things that they need to correct that I'm not quite sure about. So
And may I ask you,
yes,
the shape like that is we speak about the golden ratio. You said before about the
yeah,
golden ratio.
and we're going to get into that. So
Okay.
I'm not sure whether they strictly have the golden ratio because again they're using Lego blocks to put this together. So they could control kind of the size of the distal because there's nothing in there, but the size of those motors and everything kind of change what they are. I think they do have the golden ratio, and the reason for that is that when you close your fingers, and I will unshare just for a second so we understand it. So the idea is that when I close my fingers, you see they come in, and there's absolutely no gap between there, and my tips just come in there. If you don't have it right, you might come back in and dig in, and you won't be able to. You see, I get a gap in there that's going through. We want it to be able to close all the way, and that's why you need the golden ratio. So if your distal is too long, or if your medial is too long, and depending upon the angle it has, you may not be able to close that gap. So that's going to be something that's very important to be able to do human-like things. And if we come back here, we're going to start seeing some of the teleoperation. Okay, this is impressive. If you might remember in the video, this is just a snapshot of what's going on as a reminder. They basically took a weight and with just a two-finger grip, and that was a 5 kilogram mass, they were moving it up and down without it flopping around. And that I found kind of remarkable. And again, show and tell here with the props. This is only 2 pounds. I know it may look reversed to say 5, but it's not. It's actually I believe 2. And it's not kilograms. But think about, your two-finger grip. A lot of times when you get a two-finger grip, it's like really hard to keep it from flopping around. And that's usually why you want to have, especially your pinky. Your pinky is the most important one to kind of keep that stable from flopping around, as we can see that. But if you maybe get a hard enough grip and put it back here in your palm, you can get it to be pretty stiff. And they did that swinging around without it flopping. And that's impressive. So they get rid of these 3 fingers here, and they're able to do it. So it shows incredible grip strength right there.
Both of the motor we discussed earlier, with
Yeah,
Flexion,
part of it
the
is
small.
that, and they really held it quite well. So being able to do 5 kilograms with one without it flopping, it's like, that's not bad, showing off that kind of grip strength. And then they show after that that they can actually, when they put all of the fingers in there, they can lift up 20 kilograms. So their power grip is pretty impressive and better than there may be some tendon-based hands which are stronger, but from the standpoint of using direct drive with the motors, that's impressive. Um, Precision, again, I was not surprised by this. These fingers are tiny robots, highly precise, and they just keep on showing the repeatability here of being able to go back and forth to basically the same position again and again within 10 micrometers. That's not surprising, but still very, very good. Okay, they did show kind of like doing this with a pen. They weren't doing the whole flipping around kind of thing, which I can't even do that very well myself, but they were doing that. So it was a little bit. Don't be tricked to think that they were doing a full spinning thing. So they were getting a little bit of that in there. But they did show, the teleoperation. Now, if you look at that grip, I'm I'm trying to understand. You'll notice that the fingertips all dig in at the base of the palm, and that's not how you would grip uh, a pen at all. So if you kind of, again, let's go in here. Is that when I grip the pen, you see my fingertips are way up here because I'm trying to close that through to make sure there is no space in between. Okay. And then I want to be able to get that all the way through. Their grip seemed to be down more like that. Was down there, kind of leaving that space. So it was not as firm a grip. And I don't quite understand that for a couple of reasons. I don't think it's necessarily Fibonacci messed them up. They actually have more degrees of freedom on their fingertips than we do. So when you look at the spec sheet, you'll see that the distal joint can go 130 degrees. We can only go about 85. Okay, so when I wrap my fingers up like that, um, that that distal joint is only about 85-degree angle. You see, it's not even quite 90. I have to push it really hard to make it 90 with respect to that. The medial or the PIP joint, that one there is about, I think the maximum is 105 or something like that is what it does. Generally, the 2 of these angles add up to be like 180. So this is now kind of parallel with that. That's how it works out. So they have 130 degrees on both of them. So that means it's not that they ran out of range of motion. What I suspect happened is that they were talking about, um, the fact that they're doing this with operated control.
So you mean the human hand was part of that, like
I think the
translation?
problem is that everyone's data glove is kinda crappy. You put the data glove on there and it's bulky, and people go that, and it's not, they close it down and they can only get so much movement out of that. And it could be that if the fingers are not faithful to like the human finger lengths, the angles you're getting from the data glove result in your grip being a little bit different. That's why it's very important to get the Fibonacci, because if you are reading those angles correctly, then the gesture you get is going to be a little bit off, especially your pinky, because it's too long, not just that the proportions are wrong. But I think part of it is the tele robotic glove was probably coming on down there. Because mechanically, there's no reason why they couldn't do it. I could understand it for a tendon-based hand having difficulty doing that, but for this, like, they can go ahead and do it. So, I think the reason why it's not perfect is that it's a more of a teleoperation input issue as opposed to an output issue.
Do you think, maybe to question for the teleoperation, the glove, do you think they would have to do something to avoid this?
Oh, yeah, yeah, yeah,
What?
yeah, and they probably didn't develop their own. They probably bought one of the off-the-shelf ones that everyone else is using, and everyone else keeps on complaining the same problem. It's like, "Yeah, they're kinda good, they're not there," and of course, you could do the thing maybe with a camera, but then the camera has a problem that you get things get kinda blocked. It's kinda guessing what's going on. So, while the cameras are good for this, once you get some sort of obscuration, it's not quite sure what your grip is, and then people are using these other methods. So, there is no perfect data glove yet. I think it's a data glove problem. I don't think it's a problem with that. And that maybe if they had programmed that and said, "Hey, let's actually go into, like, do some sim the real thing here and say, 'Okay, grab this now,'" it probably would do a better job than through teleoperation. So, that's where I really believe the problem is.
And do you
Uh,
think this behavior will maybe a downside in some grasping scenario,
it's
or it
the
doesn't matter
downside
at
for
all?
everyone. It's not just for them, it's for everybody. And this is a real problem is like they talk about the sim to real. There's also like a real to sim or real to real kind of gap, and that is everyone's teleoperation stuff is junk at this point. It's they're doing some stuff, but I'm seeing and remember, we did an episode back in January showing the stuff I have. I have tons of suggestions and recommendations because I've had a chance to see quite a few setups and what's going on, and it's really clear to me what the problems are, and there's, like, some very simple procedures that could be done to clean up teleoperation, because if the data is junk, then the robot's gonna be junk. And so the same thing here is you need to have something better. But that's not throwing shade at their hand. Their hand is fine. I just think the problem is the other side, getting it. And again, if you look at this teleoperation, they're trying to do something with holding on to I don't have, a cigarette lighter, but I have a USB stick, which is kinda similar, and in the way, they're trying to put that on in there, and of course, I have to probably turn my hand around so it to be the same way. And again, their fingers are digging in the wrong place. I feel like there's a big gap. I would be holding it a lot different to be able to do that. So I did not like the way it looked like they were holding. It's still impressive they're able to strike the lighter and get that working. It shows a certain amount of dexterity, but the grip was impressive. And again, their pinky is so long, it digs in the wrong place. Okay, now finally the scissors. All right. Um, first of all, this is a left hand. I don't know why they had a right hand and they have the left hand, and so they're trying to use what are righty scissors in a left hand, and they're also kind of holding the scissors completely wrong. So either they don't know how to use scissors themselves, um, and I think the point that everyone and again, this is something that Tom first showed, and that has been showing up a lot of videos along with the Kapunji score and a few other things that I think everyone is kind of say, "Hey, this is what we have to show." And the scissors wasn't my idea; it was James Dalma's idea, and I suggested it to Tom. Now they're showing it, but just because you can hold it doesn't mean you necessarily can manipulate it. And the way it's being held is kind of wrong. I mean, so they're holding it something like that, with the thumb barely coming through, and they're using these, and that's not the way you hold a pair of scissors. Usually, it's back here because you would like to have your index finger to give you some sort of stability, and usually you dig your thumb all the way through and you pull in, and you don't just use the thumb to close it, but to kind of pull on it, because what we wanna do is we wanna get these 2 blades to kinda come in and cut the piece of paper. So, just being able to do this, I won't be able to cut anything. Something will get stuck in there, but I really can't get it. So the manipulation of that Alright, they show that they have, let's say, enough dexterity. Their thumb can go back. You see the kind of the hitchhiker's thumb there? That's rather interesting, being straight. That, um, props that they can at least get it in there, and I know someone will show a piece of paper going in there, but I don't think anyone has really done the scissors yet.
Can I ask a question? Because it seems the scissor you're holding is quite different from this one. It seems not the same.
It's
Like there's
similar.
two.
I think it's similar. I have another pair that's even bigger that you put, like, 3 fingers in there, be able to do it, but the one they have, yeah, this one's a little bit bigger because you could almost get 3 fingers in. They're putting 2 fingers up there, and then on the one down there on the thumb to be able to get it. Yeah,
Why they couldn't do it the way it's supposed to do? I think most humans do the way that you
yeah,
do it.
yeah, and again, I'm using my left hand. Usually, it would come across the other way with the right hand. I would be holding it something more like that with the right hand. I don't know. Again, it's like whoever did it maybe has never used a pair of scissors or wasn't thinking or wasn't able to get them in that frame of reference to thinking like, "Wait a minute, that's not my hand." It's just like whenever I try to help someone tie their tie, I cannot do it in front of them. I'm sitting there and like, "Oh, I have to come around from behind and have the exact same perspective to be able to do it." And it might be the same thing. It's like, "Oh, how would you get it to hold the scissors?" And then they put it in there. So they just need to have the people thinking about making the video come up with the, but they showed that, hey, look, we can hold a pair of scissors and we can make it move back and forth. But you need to show cutting a piece of paper, and it's not on an arm, so it's a little bit harder. What we want to see these things on an arm actually following a line on a piece of paper, and that would be impressive. It's like, okay, cut this thing out.
And no one can. You said you didn't see any of the demo. They can do it properly. That's
Yeah,
what
yeah,
you.
no, everyone that's showing off their hands is not showing off an arm. And a lot of these things, especially like if you wanna show writing, writing is a combination of a little bit of finger movement and the movement of an arm. So, when they do these things, like you saw that gripping demo, there was a human that basically had a stick held onto it to show the strength that it has. It wasn't eventually, they'll get these things on either an industrial robot arm to be able to test that stuff out or eventually onto a humanoid. So, they're just trying to show, "Hey, we got a hand," and if I was building a human, even if I was building my own hand for my own humanoid, I would buy this right now just to reverse engineer it or think about maybe these are the ones that I wanna stick on my arm. So there's no doubt about it. And that's what they're trying to do is that in many ways, trying to do the whole thing is very hard. And if you can find a niche, you might be able to become a pretty good supplier in that area.
I saw this post I shared with you about the reverse engineering. I think something like that, and had someone was speaking about if you have to export the design from country to another, and the reverse engineering.
Yep.
It's kind of issue about licensed technology. Do you see this concern? How this technology, every manufacturer has different hand, and yeah, that's. I'm not sure. How do
I
you
would
think
not
that?
be surprised if eventually there's some kind of standards on the hands as far as maybe an interface that, everyone's gonna wanna say, if you wanna buy this particular hand, you can put it on a bot and it has a absolute standard interface. It might be a while before they decide, or maybe like the EtherCAT that they have right now or CAN bus or something like that. So just the mechanical interface you might wanna have similar. So it might be like we do for, USB and other kind of standards like that, but it's probably too early to tell. And I don't want a standards committee doing it. I want these guys working on it, and one of them is going to come up with a hand that is really good, and they're gonna have like this interface that everyone's gonna go, "That's outstanding. Make that the standard." If you get a committee together, it's what they say, a camel is a horse designed by committee, and you don't want that. We want a thoroughbred, and the best thing is to let everyone fight it out and let the market decide that, "Man, these guys nailed it." Just like Tesla ended up kind of doing with the NACS connector for charging, is that the reason why all the other charging standards are junk is because it was a standards committee coming on in there and everyone trying to get their way. And I've been involved in a couple of standards committees looking at these things. I'm just shaking my head that everyone is trying to get their stuff in there. They're making a standard a little bit worse. And then you have these other bad actors coming in that are actually against a standard, but they get on there, they do all this, and they slow it down, and they make sure it doesn't go through because it actually undermines their business model. So it's like, nope, nope. De facto standards are the best. Look at all of them out there. It was like very small group, did it, nailed it, handed it over. So,
Do you believe what is happening now because of competition? Do you think there's some bad actors that for the business model, do you think in their best interest to stick to certain thesis or certain design? Do you think that there's maybe happening
and
by
I
this?
mean, there may be some that think they can get away with it, but the market is too smart. It's like, it might fool a few people, but in the end, if anyone is pushing like a ridiculous business model, no, eventually the market will figure it out. So you can only do that for so long. So yeah, I don't think there's any issue with that. And I think this might have been like my last slide that, down here we can see that they have, again, you don't need to read Chinese to understand this. So this is the range of motion for the different joints. So the dip and the pip, 130, like I say, is way more than we can do. And then you have the 2 MCP joints, which are basically the flexion and the abduction. To see what that is, so basically, number 2 is the abduction, 60 degrees. It basically means plus or minus 30. And then again, the MCP1 is more than we can do. I think we can only do about 90 degrees anyways, so it's going away more. And the CMC, that seems about right for the thumb. It might need to have a little bit more, but yeah, those specs are in there. And yeah, that was my last slide, believe it or not.
Well, this was really a great episode. I
Mhm,
think what struck me, all of this happening, of course, you can't catch up with all the development happening. It's just a crazy time, um, and yeah, it's just I don't know. It's exciting, overwhelming to see all of this happening at once, and you don't know how to grasp all of this info. For you, how you catch up with all of this, Scott? Like all this different.
Oh, it's really hard to follow all of it. I try my best. Like I say, there were a bunch of other hands last week. It's like, "Oh, okay, interesting, but nothing special." It's an 11 DOF, tendon-based hand. Okay, it's like under $1,000. It'd be good for hobbyists, stuff like that. I don't think I need to do a real full breakdown on it because most people, but this one was very different. And I was surprised how many people were not able to figure it out. They were surprised. Wait a minute, there's motors actually in the phalanges. That's amazing. We hadn't thought you could do that. So I thought it was like an obvious approach, and really kind of heartened that it wasn't an analysis put to waste, that a lot of people have been able to sort of open up their eyes on what the possibilities are. And this is a pretty interesting hand, especially the number of people that reached out to me and said, "Oh, when are you going to do a breakdown? When's your analysis? This is the one we all want to know about." So yeah, I think popular demand kind of helps that we get a better idea of what really is in, because sometimes I might see something that's, hey, that's cool, and everyone's like, "Nah, we're not interested." But this one, again, it's literally, I said, "Oh, it seems like it's this one struck a nerve."
It's really, really, I really enjoy it. Every time I learn new things from you, and I think it's humbling that you see the even understanding the hand. I think that's what the most
Mhm.
interesting part.
Yeah,
Understand
yeah.
biology behind it. So, yeah, and also I think of the humanoid robot in France, the Kelvin.
Kelvin,
You,
yeah,
you
Kelvin
yeah, you
40,
did
yeah,
the post about it, but
yeah.
I'm not sure if you have one quick comment. But what are your impression about it?
Uh, my impression was, at first, I probably laughed like everyone else did, and then I looked at it a bit closer and said, "Wait a minute, they're focused on the use case." So, this is like an example of more of a narrow case robot, not trying to be general purpose, but being more narrow purpose in a certain niche, where they're minimizing the number of degrees of freedom to get the task done that they want. So they don't care about being a household robot. They care about, we're moving totes around in a factory. What's the minimum number of degrees of freedom you need to do for it? And everything about it that looked a little bit odd, that hip design was intentional. Now, part of it is Wandercraft does build exoskeletons for medical purposes, so that might be part of the motivation. But the other thing you'll notice is that when it stands up, suddenly its whole torso goes back and it looks weird the way it's walking. But remember, it's carrying a heavy mass, and that thing is becoming a counterbalance. And what that does, it makes it easier for it to be able to. And that's when I said, "Oh, that's the reason that they had that crazy thing, is it to counterbalance." And they minimized the degrees of freedom in the arm. All these things. So the post I made about that was really saying that, as much as everyone might be sort of saying, "This is, I don't understand it," it's like, now I understand why they did it. And partly coming from the fact that they have already built exoskeletons, may have been they just adapted it to it. But no, there's actually more genius to that thing than you think. And it's, I think, a great exercise on how you stay focused and not distracted by someone coming and say, "Oh, but it has to do this too." And it's like, no, get out of the room. We're just going ahead and doing this. So yeah, I think it's pretty good.
You were supposed to visit them, I think.
Yeah,
And
unfortunately, they were out of town when I was coming into town, so we just missed by like 2 or 3 days. So yeah, I hope that the next time I'm over there to have a visit. But yeah.
okay, Well, that was an interesting episode, and I hope that we can have consistent episode.
Yep.
And also that when you announce, I think we should announce what we have been working on. I think before,
Yep.
aside from the podcast, so I'm hoping that we can do that
Yep.
in the coming weeks.
Yes.
But yeah, thank you so
Okay.
much.
You're welcome. Okay. Bye now.